We've always dreamed of visiting other worlds. At the dawn of the space age, science fiction imagined fleets of giant rockets would propel us into a future where the universe would open to human exploration. With rotating space stations, food grown in orbit, and frequent expeditions to planets and moons beyond Earth, the future was bright and exciting. Reality, however, took a different path. The steel giants imagined by science fiction were replaced by rockets composed of aluminium alloys, and despite the success of the Apollo moon missions, it has been 47 years since a person last left low Earth orbit. But now something is changing. In the south of Texas, a lone steel giant, a Starship, stands tall in the night, promising to fulfill our oldest dreams of venturing to other worlds. In today's Mars mission update, we're going to be taking a look at a rocket like no other, SpaceX's Starship launch system, capable of sending over 100 people to land on any surface in our solar system. We'll cover the latest design of Starship, the building and testing of the first prototypes, the timeline for future missions, and where the first Starships will land on Mars. Finally, we'll examine recent progress on building Martian outposts and keeping people alive beyond Earth in preparation for establishing a self-sufficient society on the Red Planet. On September 28, 2019, SpaceX CEO Elon Musk unveiled the first full-scale prototype of Starship, part of their next-generation launch system. When complete, Starship will be the most powerful rocket in the world, with a liftoff thrust twice that of the Saturn V Apollo moon rocket. Upon reaching space, the lower part of the rocket, the booster, will detach from Starship, turn around, and ignite its engines to return to the launch site. By re-landing the booster, it can be refueled and reused many times, dramatically lowering launch costs. After Starship enters orbit, it waits for another Starship, a tanker, to rendezvous and dock with it end-to-end, enabling the primary Starship to refuel for its journey. Once refueled, the Starships undock, with the tanker returning to Earth, while the primary vessel ignites its engines to go forth to its destination, the Moon, Mars, or even beyond. This isn't the first time we've heard about Starship. In fact, the basic concept was presented back in 2016, but over the years, the design has undergone many rapid changes and iterations, which I've documented in previous Mars mission updates. So let's start by taking a look at the latest design. The Starship launch system will be the world's first fully reusable orbital class rocket, making it 100 to 1,000 times cheaper than traditional expendable rockets. It consists of two parts, a lower booster called Super Heavy and an upper stage spacecraft called Starship. Both parts are made of an alloy called 301 stainless steel, which has the advantage of being 50 times cheaper per ton than advanced materials like carbon fibre composites, while also allowing the frame to be welded and assembled quickly without the need for a dedicated factory. The Starship itself is 50 meters tall, 9 meters in diameter, and can carry a payload orbit of up to 150 tons by mass or 1100 cubic meters by volume. At the front are two actuating forward fins, while at the rear are 6 pop-out landing legs, 2 wings, and 6 Raptor engines, 3 sea-level engines optimized for use in atmosphere, and 3 vacuum-optimized engines. Raptor is a full-flow staged combustion engine, capable of producing 2 meganewtons of thrust by burning cryogenically cooled liquid methane and oxygen. The operating temperature of this fuel, around -200 degrees Celsius, is another reason for choosing steel as a material, as 301 stainless steel is twice as strong as advanced materials like aluminium alloys or carbon fibre at cryogenic temperatures. SpaceX are currently ramping up production of this new engine, from one every 8 to 10 days at the moment to one every day by early next year. The base of Starship is coated with hexagonal ceramic tiles, serving as a reusable heat shield. For when Starship enters a planetary atmosphere, typically at 25 times the speed of sound, the oncoming airflow is ionized to produce a searing plasma that would destroy an unshielded ship. Fortunately, the high melting point of steel, around 1500 degrees Celsius, means the side opposite the flow can be left unshielded. This high melting point also reduces the thickness required for the ceramic heat shield tiles, largely compensating for the increased rocket weight from using steel instead of aluminium. Once Starship survives atmospheric entry, it descends, falling like a skydiver. The wings and fins help maintain lift, reducing the rate of deceleration and hence the heating rate. They also help to steer the falling Starship, with the actuating fins able to adjust the pitch, roll and yaw of the vehicle. Finally, Starship gimbals and fires its main engines and gas thrusters to reorient itself vertically before coming into land. The second part of the launch system, the Super Heavy booster, is 68 meters tall, 9 meters in diameter, and supports between 24 and 37 Raptor engines for a total thrust of up to 72 meganewtons. Actuating grid fins, made of welded steel, provide steering and stability during descent, while 6 rear fins at the base serve as landing legs. With Super Heavy and Starship together, and fully fueled, the total liftoff mass exceeds 4.5 million kilograms. In the most recent Starship presentation, Elon Musk estimated that the total development cost of this system is between $2 and $3 billion, with the funding to date largely coming from the private sector. Ultimately, even a single Starship could one day launch to space and return 3 times a day, or 1,000 times a year, capable of transporting over 300 times the mass of the International Space Station to orbit each year. And it is this paradox of launching more material into space more rapidly, but for a fraction of current launch costs, that will prove the game changer in enabling the settlement of other worlds. So where are SpaceX currently at in realising this vision? In late 2018, they began constructing a scaled-down prototype of Starship, later called Starhopper, to serve as a testing bed for Raptor engines in a flight environment. The goal of Starhopper was essentially similar to the Grasshopper test program SpaceX conducted from 2012 to 2013 in developing reusability for their Falcon 9 rockets, where a rocket flies to a given altitude, hovers, possibly translates, before returning to land. This overall sequence is called a hop. Starhopper experienced its first engine static fire test in April, its first flight test with a 20-meter hop in July, and finally a successful 150 meters hop with sideways translation in August. While testing Starhopper, SpaceX has also been building 2 full-scale Starship prototypes. The Mark 1 vehicle, which Elon showed in his recent presentation, has been built over the past 4 to 5 months at SpaceX's newest launch site near Boca Chica Village in Texas. Simultaneously, a second team is establishing the Mark 2 Starship in Cocoa, Florida. Both the Mark 1 and Mark 2 Starships are designed to reach altitudes of tens of kilometers, a notable improvement over Starhopper. The Mark 1 Starship prototype, shown in Elon's talk, weighs 200 tons and will support 3 Raptor engines at the base. Though the frame is mostly complete, the interior is largely empty, so the Mark 1 prototype has since been taken apart to prepare it for future flights. The next steps in SpaceX's plan is to finish the Mark 2 Starship in Florida before the end of this year, and to prepare the Mark 1 Starship for a 20-kilometer test flight as early as November or December. Should the 20-kilometer flight be successful, SpaceX will begin preparing for orbital flights. A Mark 3 and a Mark 4 Starship will be built by January and March of next year respectively, each supporting 6 Raptor engines. The first Super Heavy boosters will be built alongside this generation of Starships, ready to support the first orbital flight with the Mark 4 or Mark 5 Starship as soon as April 2020. Should the orbital test succeed, Elon Musk has stated, optimistically, that they would consider flying people around 6 months afterwards, though they would likely fly many times without people beforehand to prove the system's overall safety. Now, things get increasingly uncertain from here, so you should take these next few dates with an extra pinch of salt. A potential uncrewed moon landing could occur in 2021, largely prompted by the current political environment's focus on lunar missions. The first Mars-bound cargo missions could depart in the 2022 launch window, providing the supplies to establish a methane-oxygen fuel production facility on Mars. In 2023, SpaceX are due to fly their first paying astronaut, Yusaku Maezawa, and up to 8 artists around the moon for the Dear Moon project. Critically, a large portion of the funding for Starship's development to date has come from Maezawa. Finally, SpaceX could launch the first crewed mission to Mars from either their Texas or Florida facilities as early as the Mars launch window in September 2024. Now, that's certainly an ambitious timeline, and you'd be well within your rights to be quite skeptical that SpaceX can pull this off. But if you look back to 2016, when Elon Musk offered a similar timeline, they envisioned orbital testing of Starship in early 2020, which is only a few months off their current plans 3 years later. And given the exponential progress we have seen over the last year on Starship construction, perhaps they won't be too far off. For when Starship is fully operational, the possibilities are endless. It could help space agencies establish an international lunar outpost, mount exploration missions to the outer solar system, and progressively, over time, establish the first settlement on the Red Planet. So if we want to build a Martian outpost in the near future, one of the most pressing issues is to choose an appropriate landing site. Ideally, you want to land as close to the equator as possible to maximise the potential for solar power production. But you also want ready access to water ice, both for drinking, producing air, and for fuel, with ice more common closer to the poles. So to first order, good landing sites balance these factors by occurring halfway between the equator and the Martian poles. And because the southern hemisphere of Mars tends to be higher elevation, uneven surfaces, the northern hemisphere, around 45 degrees latitude north of the equator, is a good starting point. SpaceX have clearly been thinking along these lines, as between June and August this year, the Mars Reconnaissance Orbiter's HiRISE camera took 18 high-resolution photographs of 9 locations on the Martian surface. These photographs were tagged on the HiRISE website as candidate landing sites for SpaceX's Starship, requested in April by a geologist at the Jet Propulsion Laboratory on behalf of SpaceX. For each potential landing site, 2 photos were taken at different times to enable the construction of 3D stereoscopic images of the site, along the lines of this animation put together by the European Space Agency of a different region on Mars a few years ago. So where are the potential landing sites located? 8 of the 9 sites are found on or near Arcadia Planitia, a relatively flat region northwest of Olympus Mons. The 9th site is located in the Phlegra Mountains, northeast of Olympus Mons. Why these regions were chosen becomes clearer if we switch to a map showing the probability of water ice existing in the subsurface. In this map, put together by the SWIM project, blue indicates an increasing likelihood of water ice, whilst red indicates remote measurements are largely inconsistent with subsurface ice deposits. We can see by eye that Arcadia Planitia appears to be the best location in the Martian northern hemisphere, below 60 degrees north, to find water ice. So let's take a closer look at Arcadia. As an aside, these ice maps combine information from multiple lines of evidence, including subsurface hydrogen detected by neutron spectroscopy, satellite thermal measurements, geological signs of ice, and also radar reflection measurements. This overall provides a more robust measure of the probability of water ice than any single satellite instrument can provide. If you're interested in how this metric is calculated, you'll find more details on the SWIM project website, linked to in the description down below. If we now overlay the 8 landing sites SpaceX are considering in Arcadia, we see that they are largely consistent with a high probability of ice deposits. And we aren't talking here about a few chunks of ice, but more like a layer of ice more than 100 meters thick. We also know from impact events exposing water ice that this can be accessible within just 1 metre of the surface. Overall then, SpaceX's potential landing sites are flat, warm, relatively hazard-free, and are among the best locations on Mars to find water ice. Okay, so we've got a pretty good idea now of where on Mars to send people. So the next step is to think about some of the practical considerations for supporting a human presence there. First, how do you build a base on Mars before any people arrive? Secondly, how do you keep people alive once they are there? And thirdly, what kind of environment suits will the Martian colonists wear when operating on the surface? These are all big questions, each of which could have a dedicated video on their own. But I want to focus on some recent progress towards solving these challenges today. Classical designs of Martian outposts face a number of issues. They require prefabricated modules from Earth, making it difficult to replace modules or expand the base on demand. They also have relatively little radiation shielding, which is a big problem if you are planning to live on Mars for many decades. An elegant solution to both of these problems is 3D printing. One idea is to scout the Martian surface for local resources with robots, collect and refine the Martian regolith, and heat it with microwaves to produce construction materials. This can then be used as feedstock for 3D printing a thick, radiation-proof structure within which a base can be assembled out of flexible, inflatable modules. The design we just saw from the HASTE studio is just one of many concepts which have arisen from NASA's 3D printed habitat challenge over the past 4 years. Earlier this year, NASA's 3D printing challenge held its final competition, where 2 companies built 1/3 scale models of 3D printed Mars habitats, which were then subjected to a battery of tests. Here is Martia, the winning design by AI Space Factory. The proposed habitat is made from a material which is a blend of basaltic fibre extracted from Martian rock and bioplastic extracted from plants grown on Mars. The basalt fibre has a similar tensile strength to carbon fibre, while the bioplastic, made from polylactic acid, is an excellent radiation shield against cosmic rays due to its low overall atomic weight. The vertically oriented design of Martia minimises mechanical stresses and makes it easy for a single machine to print without having to move much across the ground, while also maximising the usable space for human occupation by dividing the volume into 4 vertical levels. Designs like this offer the potential to both solve challenges of living on Mars, while simultaneously offering a high quality of life to the early settlers. We should probably look at how to keep people alive on Mars. If you are just going into space on a short mission, it is usually fine to use consumables for life support, rather than making your own air, for example. But for a sustained human presence beyond Earth, such as on the Moon, Mars, or the International Space Station, you need a regenerative life support system. On the space station, the Environmental Control and Life Support System, or ECLSS, relies on a complicated system of chemical reactions to recycle the air and water, process human waste, and maintain comfortable environmental conditions. But this system needs routine maintenance and many spare parts, which might be able to work on Starship, for example, but wouldn't be sustainable for a Martian base. A more viable solution for life support on Mars could be provided not by chemistry, but by so-called bioregenerative life support systems. Here, plants and bacteria act in a self-contained system to recycle waste and produce breathable air, water, and food. Humans, animals, plants, and bacteria thereby coexist in a closed environment. There has been relatively little funding for such activities over the past few years, but recently China has made important advances in bioregenerative life support with their Lunar Palace 1 experiment. In 2018, 4 volunteers completed 370 days of experiments living in the 500 cubic meters self-contained facility, securing a world record. They managed to produce all of their oxygen from vegetation, recycle all water internally, and produce up to 80% of the food they consumed locally. By the time the volunteers emerged, the Lunar Palace 1 facility had reached 98% self-sufficiency. Clearly, there is a lot more work to be done before bioregenerative life support is mature enough for use in space. But these experiments are at least demonstrating the promise of such systems for future Martian habitats. Keeping people alive and well inside the base is all well and good, but occasionally the Martian settlers will need to go outside, and for this they will need surface suits, which will have to be quite different from those used at the space station today due to the different gravity and especially the abrasive dust on the Martian surface. This month, NASA put out a request for information to seek industry feedback on a new suit design for its Artemis moon program. These suits will offer increased mobility, thermal resilience, functionality in different gravitational fields, and dust resistance. Notably, NASA also explicitly mentions that the design will be flexible enough to adapt for use in the Martian atmosphere. The first of these new suits is due to be tested on the space station in 2023, ready to be used on NASA's Artemis 3 mission, envisioned to land a crew on the moon in 2024. This suit design could therefore provide a great foundation to build upon for human Mars missions in the years to come. So hopefully I've convinced you that some progress is being made on each of these challenges, none of which appear to be showstoppers for creating a human outpost on Mars. And while SpaceX are focused on developing the transportation system to take us there in the coming years, it's encouraging to see other private companies and government agencies are actively working on these important problems. Though full solutions may not be ready to support a human mission to Mars by 2024, as SpaceX are targeting, I don't think they'll be too far behind. In fact, I suspect that the rate-limiting step will be finding and training astronaut crews to go on the initial Mars missions. Because it's a very different skill set you need to independently operate on Mars than what is normally covered in traditional astronaut training processes. So you'd either have to retrain existing astronauts for many years or conduct an astronaut selection process, which I'm not aware of SpaceX having plans to do anytime soon. I'd be curious to hear your thoughts on this. Do you think anyone on Earth will be qualified and ready to go to Mars by 2024? And if so, who should go? An international team from various space agencies? Or perhaps people selected and trained by a private astronaut corps? Personally, I'd be surprised if we are ready to launch a crew to Mars before, say, 2031. But please do drop your thoughts in the comments below, and we'll get a bit of a discussion going on down there. So that brings us to the end of this Mars mission update. But since it's been a while since the last video, I just wanted to share some updates with you as to what I've been getting up to. In August, I moved to the US, and shortly after started working at the Carl Sagan Institute at Cornell University. I'm currently working on a variety of theoretical projects in exoplanet atmosphere research, including interpreting some new Hubble observations of exoplanets, which are yielding some very interesting results. In our group, we're also getting ready for the upcoming James Webb Space Telescope, due to launch in March 2021, with observing proposals due early next year. I'm also pleased to say that I'll be briefly heading back to the UK at the end of this month to graduate with my PhD in Cambridge. The next Mars mission update is currently planned to come out around the end of December, where I'll review 2019 and look ahead to next year. And given all that is due to happen over the next few months, I'll also probably organise a live stream, perhaps for SpaceX's 20-kilometre Mark 1 Starship flight. Lastly, I've also been thinking about ways to produce more regular content for this channel, which is a little tricky to balance between my research position and how long it takes to put together each video. So I'm wondering if any of you would like to be involved in future Martian colonist videos. For example, this could be researching interesting topics for scripts, designing infographics, moderating live streams, producing animations, or even if you'd just like to see what goes on behind the scenes. If you're interested, I'm thinking of putting together a Discord channel to organise and coordinate such activities. If you look in the description, you'll find a quick Google form so that I can gauge interest. So if you fill that in, I'll be in touch. There's certainly no shortage of topics to talk about around Mars colonisation, so be sure to subscribe if you haven't already, so that you don't miss a thing. Thanks for watching everyone, and I'll see you in the next Mars mission update. Thanks for watching everyone. Please do let me know if you have any questions or comments down below. To make sure you don't miss future Mars mission updates and upcoming videos, hit subscribe and click the notification bell for all the latest news on our journey to the Red Planet.